talk which has to do with both industry as well as physics, and I thought about various different ways you can divide up industry. Here's sort of from the point of view of a production manager, somehow have to bring together your capital, your labor, your feedstock. You can divide it. Instead, you can divide up industry from a more transactional point of view. So you have consumer need, you have production capacity, it lives in some sort of economic system, which could be capitalism or some sort of demand system. I'm going to take a more physics or microscopic point of view to industry. From my point of view, industry is made of three main components, which are electrons, protons, and neutrons. About almost any industry you can think of, roughly 99.9% of the mass is made up of protons and neutrons. But about a little bit less than 0.1% mass of most industries are composed of electrons, and that will be most of my talk today. So you can say I'm focusing on a relatively small part of industry, but you have to specialize. So these days, it's safe to say that we can take any particular component of industry, say the CEO of a company is made predominantly of water, and therefore of oxygen and hydrogen atoms, and these are made of protons and neutrons and electrons. But it didn't used to be that way. If we go back a little further in time, before we have our current industrial system, it looks more like this. This is about 14 billion years before the modern industrial age. There was, and in fact about 10 to the minus 6 seconds after the Big Bang, there was a hot plasma of electrons and protons and neutrons, yes, but also anti-electrons, anti-protons, and anti-neutrons. Very, very large numbers of all of them. In those days, in that microsecond, I should say, there were many more particles in the universe than there are now. Many more protons, many more neutrons, many more electrons, and also many more anti-neutrons and anti-protons and anti-electrons. They were all very hot and everything was very, very symmetrical. If we wait for about 1 second, so instead of 14 billion years ago, or 14 billion minus 1 second years ago, things had already cooled down a little bit. The universe expanded and still was electrons and neutrons and protons and anti-electrons and anti-neutrons and anti-protons, but a very festive event happened, which I like to think of as a very large wedding with many participants, many brides and many grooms, all getting married at once. And so I'm going to introduce you to some of the couples. You can see that the electron would meet the anti-electron, the proton meets the anti-proton, neutrons meet anti-neutrons. They fall in love, they get married. The marriage is very short. They disappear, and instead we have nothing but photons. And this is what happened to almost all of the mass in the universe. Almost all the electrons met anti-electrons, almost all the protons met anti-protons, neutrons met anti-neutrons, and they disappeared in a vast hail of photons. So in the great cosmic wedding, it was wonderful. There was somebody for everybody. Almost every single proton met its ideal love partner in the anti-proton, except for a tiny, tiny number, perhaps 1 part in a million, still less, of electrons that were left over, or protons that were left over, neutrons that were left over, that were not able to find their partners. And those unlucky few things, that's you. So because, I know it's a sad story, because there are these electrons and protons, a tiny additional amount of electrons, protons, and neutrons left over, they did not recombine. And in some sense, it's a good story. It's a good story because those electrons, those protons, and neutrons that were left over make up what? Industry, which is why we're here. So all that's left in the universe are a few lonely particles, and it's a very interesting and important question in theoretical physics and cosmology, if you like, to understand protons and antiprotons, neutrons and antineutrons. They're really, really similar. Electrons and anti-electrons, when we weigh them, we compare how they interact with each other. Every time we do this, we find that they're very, very similar, and yet there must have been some slight deviation from perfect symmetry in the early universe. And this deviation from perfect symmetry gave rise to the universe as we know it, so it's very important. The people who think about these things, the people who think about what could give rise to these differences between protons and antiprotons, come up with the same theories that predict differences in the early days between protons and antiprotons, also predict that the electron, given that we're sort of in this grim view of lonely leftover particles, it's not surprising that the electron should be very asymmetric, very unappealing. It's the electron that no one wanted, the proton that no one wanted, the neutron that never wanted. And the theories indeed predict that there should be, people who try to develop models to explain why the universe exists find compelling reasons to suggest that the particles that are remaining should also be asymmetric as part and parcel of the same self-consistent theory of particle physics. So what do we mean when we say the electron is hideously misshapen, when we say the electron is all asymmetric? Well, here's an introduction to the electron. It has a charge of -1, a mass of m, a spin, and therefore a spinning particle will have a magnetic moment. And we think of that as about all there is to the electron. But we could revisit it and say, at least conceptually, it's possible that in addition to this monopole moment, the electron has an electric dipole moment, an additional amount of positive charge near the north pole or negative charge near the south pole. This would give rise to an electric dipole moment, a small electric field of this shape. I like to think of it as this negative and this negative add constructively, this positive and this negative add destructively. You can think of in a charged particle as the electric dipole moment is simply a displacement. The center of mass and the center of charge are not exactly in the same place. So in my language, the units I use for measuring the electric dipole moment is just a distance. How far away inside the electron is the center of mass from the center of charge? Okay, so what might possibly be the value of this? And this is the thing that comes out of these predictions of theoretical particle physics that are trying to explain an obviously very important problem, which is why is there this asymmetry that gives rise to the universe? And at the same time, inescapably, they explain problems which are arguably less important, such as, is the electron out of round? When I say out of round, I don't mean, does the electron look like an egg? I just mean, is it somehow not spherically symmetric? Is the center of charge and center of mass displaced from each other? So everyone's favorite attempt to explain these sorts of things is called supersymmetry. And the nice thing about supersymmetry is that it predicts, SUSY, this is for supersymmetry, it predicts that the electron should have a non-zero electric dipole moment of perhaps 10 to the minus 27 centimeters, which is good because if we measure the electron dipole moment and we find something in this range between, say, 10 to the minus 26 or 10 to the minus 30 centimeters, it's very strong evidence in favor of this model, supersymmetry, and it cannot be explained by the existing model of particle physics, which predicts a value around 10 to the minus 38, 10 orders of magnitude smaller. So where does this number 10 to the minus 28 come from? 10 to the minus 28 centimeters. We can talk about the radius of the electron, the classical radius of the electron, as being perhaps 3 times 10 to the minus 13 centimeters, 3 by 10 to the minus 15 meters. This is the classical radius of the electron. It's just if you take the charge of an electron and you squeeze it down into a ball until the Coulomb repulsion is so large that that energy equals mc squared, where m is the mass of the electron. So that's the classical radius of the electron. The current limits and the interesting studies on the electric dipole moment are down around 10 to the minus 29 centimeters, which is 16 orders of magnitude smaller. What's interesting about 16 orders of magnitude? I'm not really qualified to explain to you the physics of supersymmetry. I'm not a particle physicist, I'm a molecular spectroscopist, atomic and molecular spectroscopist. But I can read Scientific American just as well as anybody else, and therefore I can explain it to you at that level. Basically, the Feynman diagram that gives rise to an electric dipole. When an electron comes in, it interacts with a DC electric field, it comes out and picks up an energy charge, and that would be an energy shift, which would be the electric dipole moment. And it arises because the electron emits, this is a great oversimplification, but it emits a virtual particle. For some reason, supersymmetric particles always start with S, like a selectron or a neutron or whatever, so I'm calling it a physics particle. And then it reabsorbs it after it's interacting with the electric field, and this sort of lowest order loop diagram gives rise to an electric dipole moment, which is small because these exotic new particles, their mass is very large compared to the mass of the electron. So it can only exist as a virtual particle, and therefore this amplitude is down, or this probability is down by this mass ratio squared. And then there are unknown factors in the theory which can be explained simply by an angle. As far as anyone knows, this angle is a random angle somewhere between 0 and 2 pi. So the sine of that is a number of order 1. So if we assume that that angle is some sort of natural value, not exactly 0, not exactly 1, let's say 0.1, then this would be sensitive, this measurement and this order of precision would be sensitive to new particles with a mass of several thousand GeV. And you should compare that to the most recently discovered particle, which has a mass of 100 GeV, which was discovered in the Large Hadron Collider in Geneva. So if you're able to do a measurement like this, you're sensitive to the existence of particles, which are, in some cases, still more massive than the particles you can observe in accelerators. So this is a competitive particle physics experiment motivated by a need to explain one asymmetry which is definitely there. The asymmetry between protons and antiprotons suggests a natural scale for the asymmetry of electrons. So we're going to go look for it. Unfortunately, many people have had this idea. They look for the asymmetry of the electron, and every time they see it, they measure a number which is consistent with 0, and the error bars get smaller and smaller. What's about to happen in the next generation or two of these experiments is it's going to get so small that if we don't see anything, life becomes very awkward for supersymmetry. Supersymmetry is a very, very popular theory, but there is exactly this much. This is supposed to be 0. This much experimental evidence in favor of supersymmetry. The only thing that it has going for it is that it's very beautiful. But if you have to impose all sorts of restraints on it, such as, oh, it's very beautiful, but it has to be specially fine-tuned to give the electron a small dipole moment. Oh, it's very beautiful, but it has to be specially fine-tuned to give the neutron a small dipole moment. Then it's less beautiful. And that's all we can really do, is just we can't really kill the theory, we can just make it less fashionable. So we're trying to influence the fashion of physics, if not the actual truth. Of course, if we see something, that would be very nice. So, sorry to say this, but I've been working on this experiment for 10 years. It turns out to be rather difficult. I have a group of very talented graduate students, Kevin, Matt, Will, Dan, and the undergraduate, Michi. It's a sufficiently complicated experiment that I do it jointly with another professor, Jun Yi, who's also like me a NIST employee. So the two of us are both NIST employees and CU professors, and we've been working on this for quite a while. We've also been fortunate to have in the past other very talented graduate students who have measured 0 and gone on to better careers. Okay, so how do you measure an electron-electric dipole moment? To measure the electron-electric dipole moment, we could ask ourselves, how do we measure the electron-magnetic dipole moment? That's a very simple experiment. That's simply ESR, electron spin resonance. You put an electron in a magnetic field, you get an energy for spin up, an energy for spin down. You shine radio waves at the electron, and if the radio waves are the right frequency to account for the energy difference between the magnetic moment pointing against or with the magnetic field, the electron flips over. You do a resonance study, and the center of the probability of the electron flipping, the frequency which maximizes that is just the magnetic moment the electron times the applied magnetic field. Very easy, very standard thing, industrially relevant as it turns out. For an electric dipole moment, we add, in addition to the magnetic field, we add an electric field. If there's an electric dipole moment, then you would get a magnetic energy and electric energy, and the line will shift. If we do the experiment again with the electric field pointing the other direction, we'll see the center of the electron spin resonance line move back and forth a little bit, and the amount it moves back and forth, if we subtract the center of this line from the center of this line, the magnetic field is canceled, and we're left with just a measurement of the dipole moment of the electron times the electric field. Conceptually, it's a really simple experiment, and people have done simple versions of this long ago, and they found zero, so we want to do a better version. What makes a good electric dipole moment experiment? Well, first of all, you want to apply a really big electric field. The bigger the electric field, the better. Second, you want to have a long coherence time. Spectroscopy along coherence time means narrow resonance lines. You can determine the difference between this line and this line. You can do better if you have a long coherence time and the lines are narrow. And then finally, you want to count many spin flip events. And by doing that, you can determine the center of the line to much better than the width of the line by a factor which is about equal to the square root of the number of particles you count. So combined, we have a figure of merit: effective electric field, coherence time, number of count rates, which you can observe in the lifetime of a graduate student, which is the fundamental unit of time in an experimental physics lab. The problem is, if you take an electron and you put it in the big electric field, the electron goes, it disappears. So that would be a very short measurement, a very quick measurement, right? So you need to do something different. The standard solution is, instead of doing this experiment on a bare electron, you would attach the electron to a heavy atomic nucleus, so now it doesn't move very much. You do the experiment there. There's a relativistic effect, which is proportional to the charge of the nucleus to the third power, so that the effective electric field applied to the electron can be larger than the electric field you apply in the lab. And because the atom is heavier, you have a longer time to make the measurement. The other thing you can do to make the electric field very big, and this is what we do, is we put instead of just using an atom, we use a molecule. I was never really trained in chemistry, and I didn't study molecular physics as a graduate student. I had to learn molecules later on. From my point of view, molecules are just nature's way of applying a very large electric field to an atom. So, for instance, say this atom here is fluorine. Fluorine is very electronegative. If you attach a fluorine atom to anything else, the fluorine is negative, and it applies a very large electric field on this atom. And if there is the electron spin, in effect, is living in this region between the two atoms, it can experience a much larger electric field than you would apply in the lab. So instead of, if you apply maybe 10 volts per centimeter in the lab, which is enough electric field to polarize the molecule, you get effectively perhaps 9 orders of magnitude larger electric field applied to the molecule. It's like an amplifier for electric field. Molecules are great in that respect. The other thing is that we want to have a very long coherence time. My whole career has been cooling and trapping atoms mostly and putting them in traps and keeping them for a long time and making Bose-Einstein condensates with them. Cooling molecules and trapping molecules is quite a bit harder than trapping atoms, at least if you use neutral molecules. But it turns out that trapping ionic molecules which are missing one electron, that's relatively easy to do. Ion traps are relatively simple technology. I actually did it as a graduate student in the 1980s, back when there were vacuum tubes in the laboratory and strip jar recorders and things like that. So you know it has to be pretty easy to do. I won't run you through this chart, but there's a number of other groups that are working on it, and I mentioned in particular the ACME collaboration, which is a Harvard-Yale group, which recently made a measurement in thorium oxide, which has an unpaired electron spin. And they have the current limit, which is if the electron's electric moment exists at all, it is less than about 10 to the minus 28 electron centimeters. This was an enormous increase, about a factor of 10 or more in precision over the previous measurements. which were done first at Berkeley and then in London. This is what our ion trap looks like. I put up this picture mostly because it looks nice. It's a little, the ion trap is actually covered with gold. It's actually made out of aluminum, but it's covered with gold, so it's very shiny. And you can see here an electrode, and here's another electrode. The distance between there is about 10 centimeters. It's a relatively large ion trap by modern standards. But the thing about an ion trap is that its job is to apply electric fields which push the ions into the middle of the trap. Therefore, by definition, it's not an ion trap unless the electric fields are very inhomogeneous. Particularly, ion trap electric fields have to be inhomogeneous and time varying in order to trap ion. And you would think this would be the worst possible place to do precision spectroscopy in an environment where the electric fields are inhomogeneous and time varying. Fortunately, there was a wonderful idea introduced by Dave DeMille, now at Yale, to use a certain class of molecule where you could do spectroscopy on the molecule. You measure two different lines in such a way that you cancel out all the unknown factors of the magnetic field, you cancel out the unknown factors of the electric field, and all that's left is the electric dipole moment. So here's the lowest state of a triplet delta 1 state of a molecule has angular momentum 1. So this is mj equal 1, mj equals 0, mj equal minus 1. And it comes in a parity doublet. So each state, like m equal 1, is either in a symmetric combination of the molecule pointing one way or pointing the other, or in an anti-symmetric combination of the molecule pointing one way or pointing the other. When we apply an electric field, these states mix into each other. Now they are no longer states of parity, and the molecule is pointing up in the electric field or pointing down in the electric field. If we then apply a magnetic field, it splits that degeneracy. In the absence of an electric dipole, that transition there is going to have exactly the same energy as that transition there, independent of whatever the electric field and magnetic field is. So we measure those two lines, we subtract them, and we don't have to worry too much about what the electric field and magnetic field is. If there's an electric dipole moment, an electron living in that little space in between the molecules, it shifts that line up, that line down. It shifts that line down, that line up. And now those two transitions are slightly different, and we take the difference between them. We get 4 times the electric dipole moment that exists times the effective electric field inside the molecule. Everything else drops out. So it's possible to do this very high precision spectroscopy in an ion trap. Let me see how we're doing here. We spent a lot of time. So I come from an atomic physics tradition, and moreover, I work at the National Institute of Standards and Technology, where atomic physics has a very long background. NIST, and before that, National Bureau of Standards, would publish this table. It's still available online of atomic spectra. There are about 100 different elements, and you can go online and you can find all the different laser transitions you care to know about. And you also can do a lot of theory and a lot of experiment done on the atomic structure. If you go just one more atom more complicated, if you look at a diatomic molecule, there are 10,000 neutral diatomic molecules, roughly speaking. If you include positively charged and negatively charged, singly positively charged, singly negatively charged, there's about 30,000 different molecules with 2 atoms in them. For about 90% or even more, 95% of those different possible molecules, there's never been a scientific paper written, no measurement done, no theory calculated. So trying to find the ideal molecule which has all the perfect properties turned out to be a lot harder than we thought it would, but we had to engage powerful theoretical help from the sort of Russian tradition of molecular structure, calculated molecular structure, and we had to do a very large amount of our own spectroscopy in-house. And the spectroscopy we did was very sort of 1950s spectroscopy, the surveying thousands of molecular lines from different species and thinking about what they meant. So I felt like I was getting back to my roots as a spectroscopist and doing this. which was good because I had wandered far away from the farm and was studying ultra-cold atoms and spending all my time talking to condensed matter theorists. Finally, I came back and was talking again to other spectroscopists. I felt like I'd come back into the farm. I was welcome to the Little Arms. They didn't reject me. You would think that it was nice. Anyway, I'm not going to talk too much. It turns out that a particular ground state of the molecule, the triplet delta 1 state, I'm not going to describe exactly what that means. It turns out that many, many good features, which makes it ideal for the study of this kind of study. And in particular, the triplet delta 1 has a very small magnetic moment, which is good because if we have random noise on our magnetic field, if you have a small magnetic moment, you don't get noise, you don't get the line broadening. And one of the most important systematics in systematic errors in this sort of business is proportional to the electric field you apply in the lab times the magnetic moment divided by the effective electric field. And compared to the original atomic experiments, pure atom experiments, atom beam experiments on this, working in a state like this gives you a 9 order of magnitude improvement to the point where even though we're doing a very precision experiment, we don't have the traditional anti-magnetic magnetic shielding wrapped around our experiment. It doesn't look like a classic precision measurement experiment in that respect. So our friends Angela, John Bone, and the student Ed Meyer spent a lot of time thinking about the right kind of molecule. And it turns out in the end, hafnium fluoride plus thorium chloride plus were the ones that we're using. Thorium fluoride plus is ever so slightly radioactive. So there's a lot less paperwork to use hafnium fluoride plus. When the safety officer from the University of Colorado came to inspect our system to see whether we were sufficiently safe against radiation poisoning, I pointed out to him that it's not actually possible to die of radiation poisoning from eating thorium because the chemical toxicity is so high that the dose which will give you radiation poisoning will kill you on the short term of chemical toxicity. And you would have thought that would have made him very happy, but it didn't. So here's what our experiment looks like. We have a little bottle full of sulfur hexafluoride. There's the fluorine and neon. A little lump of metallic hafnium. We zap it with a laser. We make hafnium fluoride and hafnium fluoride plus. And they come flying out. And the neutral hafnium fluoride molecules come in here. We actually take the ions away. So now this is supposed to be our ion trap. And in the middle we have some neutral hafnium fluoride molecules. And if we zoom in on there, we see that it looks like neutral hafnium fluoride, but if we actually look at the molecule, there's many different isotopes, many different vibrational levels, many different rotational levels, hyperfine, to the point where one finds that any given single quantum state has an occupation number of only about 1 in 1,000. And the actual experiments we do are from one precisely specified quantum state going to another. The other 999 ions are all just background collisions causing us trouble. So we come in with a laser and we go to a back-bound transition which selects out just a single rotational level and a single isotope and a single vibrational level. We go to a higher level which auto-ionizes, and it creates a hafnium fluoride plus molecule which is an ion, but in a much purer, perhaps 50% of the ions are all in a single quantum state. So now we have much less impurity ions floating around in our trap causing trouble. So there's our ion. It starts in the true ground state. The state we want to be in, the molecular state, is called the triplet delta state. There's no atomic dipole transition. You can't just shine a laser beam and move the molecule from this state to here. But we can go by 2 molecules up and back down again, and two lasers, a laser beam up and laser beam back down again, and coherently transfer much of the population from here to here. It's a technique which Jun Yi, my colleague at Jill, is tremendously good at, so this was a natural fit for us. If I look inside this state, I see that it's actually, here is the science state I was talking about, the different projections, the different M levels. By adjusting the relative frequencies of these two lasers, I can populate one state or the other state, and by adjusting the polarizations, I can pick whichever the initial state I want to be in. Then I can do my radio frequency spectroscopy. I can apply a pulse, split the population up, wait a little while, apply another pulse, see what happens. This is the so-called method of Ramsey's separated oscillatory fields. And then we want to ask the question, is the ion in this state or is the ion in that state? And that way we can measure the frequency difference between these two states. Our original idea is we would shine in a laser beam, which was circularly polarized, to a state up here which has only n equals 0. So if the ions were over here, they would absorb that photon and emit a photon which we could collect on a detector. If they're over here, there's no state up here, so this transition is forbidden. So basically, we only detect the ions in this state and not the ions in this state. The problem is laser-induced fluorescence is a very inefficient way of detecting molecules. And so we decided instead to use this technique to simply depopulate molecule, pump away all the population except for the population of this state. And so now I just have molecules in the J equal 1. To determine if they're in the J equal 1 state, we do a resonant process with 2 more photons to go through an intermediate state in hafnium fluoride plus and finally into a dissociating state. So it's a long sort of chain of contingent events, but if our radio frequency is resonant with the transition, then it makes a Zeeman level transition, and then it absorbs a photon and falls out. If it doesn't absorb that photon, it can absorb these 2 photons, and then the hafnium fluoride plus molecule breaks into hafnium plus and fluoride. And it turns out that if you have ions in a trap, some of them have the mass of hafnium fluoride plus, and some of them have the mass of hafnium plus. It's really easy to tell which one is which. Here's our ion trap, and there's our hafnium plus, hafnium fluoride plus. We just dump them out. They fall onto the detector. The lighter atoms fall faster, and get accelerated faster. We see them sooner. They arrive. The hafnium plus atoms arrive only 30 microseconds after we dump it out. The hafnium fluoride plus arrive 35 microseconds, and we can with very little background, we can detect which state they are, which tells us whether or not they photodissociated, which tells us whether or not they absorbed this RF photon, which tells us what's the frequency of that transition, which is what we're trying to do. It's very complicated. It's 7 lasers have to be running all on the same day, and they're all tend to be relatively high performance lasers, so it's a difficult experiment, but it helps to have 2 professors and a lot of very talented graduate students. Our laboratory looks mostly like a room full of lasers. It's hard inside there to actually see the ion trap, which is way back there somewhere. Everything else is just lasers. So there's one more trick I want to discuss, and that is it doesn't take very much electric field to stretch out the molecule, but it still has to be a non-zero electric field. The molecule left to its own devices will be rotationally symmetric, so you need to apply a small electric field of 10 volts per centimeter. The whole point of an ion trap is it tends to trap ions at the place where the electric field is 0. So what we did is we applied a rotating electric field. The electric field rotates, it's a uniform bias field, it rotates at time. It rotates slowly enough that the bias, it rotates rapidly enough, I should say, that the molecule doesn't go very far before the electric field causes it to turn in a circle. So basically the ions are traveling in tiny little circles inside the trap, radius of perhaps 1 millimeter. But it rotates slowly enough that the quantization axis of the molecule is able to track the rotating frame, and we just do our spectroscopy in the rotating frame. There turned out to be a lot of subtleties associated with doing spectroscopy in the rotating frame. That's something we spent a lot of time studying. Here's just some of our data that we took on the way. Here's the surveys I was telling you about doing survey spectroscopy. We cataloged more than 10,000 lines in hafnium fluoride plus. Also now at thorium oxide plus and thorium fluoride plus. There's our ion trap. Inside the ion trap, in taking the atoms from the singlet sigma up from triple delta, this energy difference is sensitive to the hyperfine difference. I didn't mention this, but it complicates things. The fluorine atom has a proton splits up the state. So we can measure the hyperfine splitting of that. If we apply an electric field, the hyperfine manifold breaks up into different Stark levels. These are the levels we care about, and we see them, the 1, 2, 3, 4, 5, 6 levels, as we sweep the frequency difference between these two states. We change the amount of population, and we move up to these various different molecular states. And we can map that out as a function of the applied electric field and get the Stark shifts, map that, and from this extract the polarizability of the molecule and other useful data along those lines. So, actually, I think I want to tell you about how we do these, exactly how we transfer. Basically, we use a radio frequency technique to move the molecules over there. And we are now actually seeing these Ramsey fringes, these spectroscopic fringes on the transition. Because we apply a very small magnetic bias field, our transition is about 41 hertz. We're looking for tiny shifts in that line of about 1 millihertz. You can see so far our resolution isn't quite good enough, but we're getting there. Our coherence time is almost half a second. We've measured the lifetime of the metastable state and found out that it's 2 seconds before it decays. That tells us that we could do better than a coherence time of half a second. We could do at least a factor of 2 better. And we think we understand why we're not realizing the full coherence time. Things are very promising. We measured the magnetic G factors of the molecules. We have an estimate of the sensitivity, which tells us that in just a single day of collecting data, we should be able to be competitive with the current best measurements. If we integrate over several tens of days, we should be able to do a better measurement. Of course, in these sorts of experiments, everything comes down to systematic errors. A lot of what you want to do is sort of change the direction of the electric field, change the direction of the magnetic field, change the direction of the rotation, change everything. The science signal should depend on all these different changes, or chops, as they call it in the business. In a particular way, the systematic errors will depend on this in some other way, and in this way we can figure out what's the real science signal and which are the errors which are tricking us. We think that we have enough of these chops, and as the jazz musician would say, we've got the chops. We can make this measurement and get very low systematic errors. And we haven't yet been able to think of a systematic at the 10 to the minus 28 level. And if there's smaller ones that we haven't predicted, we have a lot of powerful techniques for smoking them out, for finding them. So if we do find that, and we find out that the electron is out of round, the implications are, well, it's different from having an out of roundness and a ball bearing in your industry. If your ball bearing is out of round in your industry, then your turbine won't stand or whatever. But if your electron is not out of round, there's a real chance that the turbine doesn't exist at all. So it strikes me as an industrially relevant measurement. I thank you for your attention. Yes?
I was curious as to if there are any measurable precision in whenever you have your electric field. Hello? Okay. So I was wondering if